of more than 40 people over 2.5, almost 3 years now. And we are quite pleased with how it worked out. So my task today is to set the stage for what's coming in the week ahead. I'm going to talk about the motivation for the project, why we did it, and what the main results are. All details will be deferred to the other talks by individual members. So I will just go for the high level stuff here now. And as the title says, BeyondPlanck, this really is based on Planck. So Planck, as you know, was ESA's cornerstone mission, satellite mission that was observing the universe between 2009 and 2013, observing the sky in 9 frequency bands between 30 and 857 gigahertz. 7 of those bands were polarized. And to me, these 9 maps here really is the main outcome of the Planck project. But of course, what really pays for the mission is what you see up here, these fluctuations that has the same strength in all these frequency channels, and that is called the cosmic microwave background. And of course, you have all seen this before. This is a map of the primordial universe just shortly after the Big Bang, 380,000 years after the Big Bang. This is really what pays for all of these kind of missions. And Planck was spectacularly successful in measuring this. Using these observations, these constraints on the cosmic microwave background, the Planck mission team was able to constrain the evolution and content of the universe to unprecedented accuracy. You can see the power spectrum here plotted against the model, and it fits spectacularly. These are the things that, measurements that give us things like how much dark matter there is in the universe, how much dark energy, when the first stars were born, and so on. And so Planck really is a bedrock of modern cosmology. It's a cornerstone mission. There's no doubt Planck was a spectacularly successful mission. But at the end of the mission, there were still a few issues that were left. We were not completely able to resolve. There were some systematic errors. There were some open questions that were still to be resolved. And so one of them is illustrated in this particular plot from a 2018 paper, the legacy paper, which simply shows the difference map between the 30 gigahertz channel in Planck and WMAP K-band. And what you can see here is that there are large-scale structures. The Planck team was, of course, working hard on eliminating systematic effects in the last years between 2015 and 2018, and you can see that things got better in terms of agreement with WMAP. We did understand issues about the instrument, but there were still issues to be resolved here, either coming from WMAP or Planck, we don't know, but clearly there were differences. One of the issues that were critical in the last Planck release was to understand the calibration of the instrument, the gain. And that is illustrated in this form here. What is shown here is essentially the LFI 30 gigahertz gain as a function of time throughout the mission, and see how that changes in time. And for 2 different gain models, 2 different calibration models. And you can see the black one, that is what we had in 2015. And the red ones are essentially 4 different gain solutions that were used in the 2018, which shows less fluctuations and overall better stability than we had in 2015. But what is interesting to see here is there are 4 different cases, and those correspond to different foreground models, essentially. So one of the things that the Planck team realized and really pushed on in the last part of the mission or experiment analysis phase was the fact that in order to understand your calibration, you really need to know what the sky is. So you have to account for foregrounds, you have to account for systematic errors together with the foregrounds. And so what these 4 different cases are is essentially iterating in the sense that you produce a temperature sky model, you use that to correct your data and then improve the gain. You use those gain to produce a better sky map and then a better foreground model. And you can see that we managed to do 4 of these, and each of those iterations took about 3 weeks. So it was a long process. And you would hope that it's going to converge eventually, but you can see that there was still some drift here when we essentially ran out of time. And that is what's illustrated here. This shows the difference between two of these iterations, essentially. And you can see that there are large-scale modes here that the Planck scanning strategy wasn't able to resolve, and this is what is often called poorly measured modes. And this is what it looks like for Planck, and this is null. So Planck, when it finished, we knew that we have uncertainties at this with this type. Of course, for comparison, going back to WMAP has a similar kind of poorly measured modes, and they published that. So if we now look at the original difference map that was plotted in the 2018 paper, you can see that, well, this is the difference, and it actually does correspond to those well understood effects. Of course, we would like to resolve this and improve these calibrations, and that is what BeyondPlanck is about, trying to understand these features. So the starting point for BeyondPlanck was essentially, first of all, we realized that doing component separation and gain calibration by hand with a turnaround time of 3 weeks or something like that is painful. You can't do a lot of them, and you can't converge properly. So the starting point was, what about how can we automate this and remove all human interaction so it actually can speed up the process and perform hundreds of these iterations? It's not just 4. The other one is that, well, recognizing that Planck has degenerate modes, WMAP has degenerate modes, is it possible to combine the two and sort of use one experiment to break the degeneracies in the other? And that is essentially what BeyondPlanck, the name, is chosen to indicate. So first of all, recognize that this work builds on and is a natural continuation of the Planck analysis effort. What we're using here is known information from Planck and trying to integrate that into one code that can do the whole thing automatically. The other one is that what is new compared to the Planck effort is that we're not using just Planck data, but we're actually integrating other data sets, in particular WMAP, into the analysis. So it's not just Planck, it's BeyondPlanck. It's WMAP and other experiments as well, all integrated into one pipeline. So why do we care? If all of this was just about improving, say, the existing Planck channels, well, that would be an important goal in its own, but that's really not what motivates us. What the motivation lies is the future, to go for a primordial black hole, not black holes, primordial gravitational waves. So as you know, a few years ago, LIGO made the first detection of gravitational waves from black holes. And what the field is such, the CMB field is working towards now is to find the same type of gravitational waves from the Big Bang. And that's really what is driving us. Use the experience we got from Planck to prepare for the future. So go beyond Planck. And to illustrate what this is about, here is a simulated map of gravitational wave signals in the cosmic background for one particular model. And this model is often parameterized in terms of the tensor to scale ratio, which says how strong are the gravitational waves compared to the normal density waves. And this is for a ratio of 0.01, which is relatively high. It's within the limits of you're allowed by today's constraints. So, but it's optimistic. More realistic is probably 10 to minus 3, 10 to minus 4, something like that. So this looks all nice and well. People are working with CMB, are familiar with this kind of structures. Everything looks good. The scary part is when you put a color bar on it, because then this is actually plus minus 0.1 microkelvin, 100 nanokelvin. And as I said, I mean, this is optimistic. Probably it is 3 or 10 times lower than this, which makes it even much harder. So why is that a problem? That is a problem because the actual sky looks like this, and the color bar here is plus minus 3,400 microkelvin. So that means that we're talking about 4 orders of magnitude, digging into the signal 4 orders of magnitude, and you have to clean out everything you see in this map. So you need extremely accurate control on component separation and systematic effects. That's really the name of the game here. So if we're now looking at the sky again, what does that mean in practice? Well, if you take the sky and you peel that CMB dipole off, that's about 3,400 microkelvin. You do the foregrounds, you're left with the foreground signal that is about 1,000 microkelvin. If you do that, you're left with CMB temperature fluctuations, 250 microkelvin. Peel that off, and then you're left with something that should hopefully be noise alone. And this is for the Planck 443 GHz channel. And you can see that it's spectacularly accurate. It's plus minus 2 microkelvin. It's brilliant. But still, you see these large-scale coherent structures here that is actually still 20 times larger than what we need in order to dig into R of 0.01. And this, again, is optimistic. So that sort of illustrates the challenge we're facing here, getting rid of these kind of effects here to see that tiny signal after all of that has been removed. Here's another illustration of the same point in terms of angular power spectrum. Up here is the normal density fluctuation that Planck was designed to measure and really did very, very well. What you see down here is galactic foregrounds. So thanks to just scanning around for this plot, by the way. Here are the foregrounds. This is where we expect polarized foregrounds to be. But what we are looking for is the gravitational wave signal, which is down here. And it's many orders of magnitude below the temperature signal. And if the only problem was galactic foregrounds, we could deal with this, I think. We have pretty good methods these days to handle that. The problem arises when you have instrumental systematic effects. And from Planck, we know that for Planck, it's roughly at this level here, where you can barely see the reionization peak down here. And down here, there's essentially this swamp of interplay between instrumental systematics and foregrounds. It's not either one, it's a combination of them that really makes this challenging. So in a sense, we have a classic chicken and egg problem, because the CMB data that you have here, they do have a lot of signal from the sky. That's what we want. But of course, it's not just the sky, it's actually the instrument as well. So what you actually observe is the sky multiplied by the instrument calibration, essentially. And if the uncertainty is here, well, then you don't really know what's happening here. So you can summarize the problem as follows. In order to measure the sky, you need to know the instrument at the level of 10 to minus 4. That's what we looked at before. But in order to know the instrument to a factor 10 to minus 4, you also need to know the sky to 10 to minus 4 in order to calibrate the instrument. If the calibrator, which is this signal up here, is incorrect by 10 to minus 4, well, then you have the same problem here. So you have classic chicken and egg problem. Where do you start? And if you then take a look at what a classic CMB analysis pipeline does, then it looks something like this. You have the CMB telescope producing data and coming out uncalibrated in some kind of units. You want to calibrate it and you want to produce frequency maps, and that's ending up to something like this. Then you plug that into component separation code and you get CMB and thermal dust and CEO and synchrotron and all the things that the sky consists of. And then you take this map here, you compute the CMB angular power spectrum, get these data points here, and finally you compute the cosmological parameters based on that. So this is the classic problem, or classic analysis pipeline. What Planck sort of realized is that the errors you get up here is really dominated by foreground uncertainties here pumping into this level. So the connection between calibration and component separation is really, really tight. This is where we need to add something new. And the solution to this is quite simple, as was realized by both HFI and LFI during the end of the last stages of Planck. You have to take the information that you learned here and feed that back into this process here. So, you know, in a way you can solve the problem is if you just add another arrow here and you use what you have learned up here and into the calibration. And this is what we mean by end-to-end iterative analysis. And of course, as I said before, normally each of these maps stages here has been done by individual human interactions, essentially. So somebody was responsible for calibration and producing maps, sending that off to component separation. Somebody else was responsible for power spectrum estimation and then parameter estimation at the end. And that makes for a very, very slow turnaround time. This can be months in a single iteration like this. And what BeyondPlanck is about is now building one machine that does the whole thing and speed it up and being able to operate in this framework faster. So the BeyondPlanck project, the main goals of what we proposed to do was, first of all, we want to implement an end-to-end analysis framework for current and future CMB experiments using what we have learned from Planck. That is by far the most important goal of BeyondPlanck. The second thing is that we want to demonstrate this on Planck LFI data. So LFI was chosen because it's relatively small in data volume. It's well understood, especially by the team members. And we were confident that we could work with this on a 2.5 years time scale. And it had to be fast because of the constraints in funding. We also want to make this software and results publicly available under open source license because, as I said, we want to go forward. Our main goal is not to apply this to Planck LFI, but actually go beyond Planck into the future. And we want to sort of provide this to other experiments and build a community around this. So the BeyondPlanck collaboration has been funded by the EU, as Anastina already mentioned, and Originally, there were 5 main institutions: Oslo, Milano, Trieste, Helsinki, and Planck. And then later on, we got invaluable contributions from a number of external collaborators as well. So if we're now to look at the BeyondPlanck pipeline in a single slide, I'm very happy with this, this picture actually, because it's the simplest way you can approach CMB analysis in my view. What you do, or what we do, is to write down an explicit parametric model for the observed data. And I'm going to talk more about this on the next slide. But essentially, you have the time-ordered data over here, and then you write down some model mathematically that should hopefully capture everything that is important in the data. And then there are 3 parameters here that we're going to fit. So let omega be the set of all 3 parameters. Then we write down the expression for the joint posterior distribution using Bayes' theorem. So what is the probability of finding all those parameters given your data? And that is, by Bayes' theorem, simply the likelihood times the prior. And I'll be talking about that shortly. Then we use standard Markov chain Monte Carlo methods to map out that posterior distribution and get all the parameters jointly. That's how we do it. Quite simple and direct and very, very straightforward. So if you're looking at the data model again, so we have the data over here, and that's the uncalibrated time streams coming directly out of the instrument. That can be written as a sky model, so sum over astrophysical components, and CMB will be one of them, and synchrotron will be another one. This is a mixing matrix. And that says how bright is the given component at some frequency. Then this sky model is seen through a beam, essentially, a point spread function. The satellite is scanning, so there's a pointing operator here. And finally, there's a calibration factor, a gain in front of that is time variable. Then we have some very systematic effects. The band pass, for instance, is not perfectly known, so you have to calibrate it, and we have to fit for that as well. There is side lobe pickup with asymmetric beams. There is an orbital CMB dipole. There's correlated noise, and there's white noise. So this for LFI is a fairly complete model that seems to be working very well, as we will be discussing. But this is really what we're fitting to the data. So of course, the sky model plays a special role here, and the model that we are using is again a parametric model. It's explicit that consists of CMB, synchrotron, free, AME or spinning dust, thermal dust, and point sources. So the sky, of course, has other components as well, like the CIB or SZ. We are neglecting those because we don't have very high signal to noise to them. So in a future version of this, where we did HFI as well, this would be expanded with CO and other components as well. But let's then call omega be the set of all of those 3 parameters. And then Z, the posterior distribution, is given as the product of the likelihood and the prior. And the likelihood is very simple, actually. It's simply data minus a signal model. That is Gaussian noise. So if you take data model on the other side, you subtract everything in this model here, put that on the other side, you're left with just white noise. And therefore, you have a standard Gaussian distribution with white noise covariance in here. And now correlated noise is actually part of the signal here. So that's an unusual point that we'll come back to later in the week. For the priors, that's less easy and less trivial. This is very much up to individual users. What are your preferred priors? And just to take a few examples of what we have chosen to do here, and you can argue with that, and you can then rerun with different priors. To describe the correlated noise, for instance, we have used in previous estimates from the LFI DPC, but we are allowing for uncertainty in it. So we use a normal distribution for that. For the spectral index of synchrotron, we are using literature values of -3.1 plus -0.1, but we are testing for dependency, so sensitivity to that as well. For the thermal dust, we don't have any sensitivity to thermal dust with LFI, so in that case, use a delta function that is just fixing it to the most recent HFI estimate. Future analysis with HFI should then get rid of this and just fit it directly. Free and AME, there we also use informative prior, and this is a new thing in the current analysis, in that we use spatial priors for this. And essentially what we're saying is that the free amplitude should be close to what Planck measured using also HFI data. HFI is really powerful for free. So this is a way of integrating HFI information into the process without actually having the sky maps, which would then dominate the CMB. So here we're getting help on the free without dominating the CMB, which we don't want to do, not yet. For AME, we're saying that it should be probably closely correlated with 857, which is a dust tracer. but allowing for a free amplitude and uncertainty. So all of these are uncertainties. So we're not saying that it should be equal to them, but it should roughly fluctuate around it. So if the data doesn't have a constraining power, it's going to default back to those priors. So how do you fit this big distribution? Because now this is going to be billions of parameters with the correlated noise and everything. And this is where Gibbs sampling comes into play. I'm not going to go through that in detail. I recommend you to read about Gibbs sampling. It's a really useful and powerful method. I'm just going to illustrate it briefly using this picture that we just had. So what do we want to do? We want to have this iterative loop here going round and round and round and improve the results over and over again. This can actually be phrased in a statistical, rigorous language in terms of Gibbs sampler. And the Gibbs sampler can be written mathematically as this. So what we do in practice is that you have a joint distribution, and then you fix all other parameters except one. So here in this first one, you just focus on the gain, and you assume that you know everything else in the system. You assume for now that you know the sky, you know the gains, no, not the gains, because that's what you're sampling, you know the spectral indices, you know the band passes, you know the correlated noise, whatever. And then you draw a sample from that distribution. Then you fix that one, and now you sample just the correlated noise, and while fixing the gain. Then you can sample the correlated noise parameters while fixing everything else. Then the bandpass parameters, fixing everything else. Spectral indices, fixing everything else. Amplitudes, fixing everything else. And the cosmological parameters, or the CLs, and fixing everything else. And then you start again, and you go around and round and round and round until you converge in a probabilistic way. So this is a formalization of this iterative process. And according to statistical theory, it's guaranteed to converge to the correct distribution as long as you're sampling long enough. And what this paper is about is essentially describing the various steps and results that come out of that. And again, I'm not going to go into any details. There is a lot of algorithmic breakthroughs in these papers. There's a lot of material, and there's going to be a lot of fun over the next few days. But I'm going to leave it for now and just pick out a few highlights in terms of results. What does this give us? Before doing that, though, I want to say a few words about data selection, and that is just emphasizing what I just said, is that our main focus here is Planck LFI 30 gigahertz, and 30, 44, and 70 gigahertz. And really our main topic is the algorithm itself. We want to illustrate how the algorithm works. It's not about producing the best possible sky model. If that was the case, we would have included HFI, we would have included other data sets. But we want to illustrate what the method does, and then in the future it's going to be expanded with all these other data sets. So we are using Planck LFI, that's our main goal, and that's the only thing we do in time order data for now. But then we also add a few other data sets because we don't have enough statistical power to constrain the whole model that we just talked about with only LFI. And the data sets we include is Planck 857, and we include that in order to constrain thermal dust in intensity. We also include 353 gigahertz in polarization to constrain thermal dust polarization. We don't have much sensitivity to that alone. And we also include WMAP between 33 and 61 gigahertz in both temperature and polarization, and that is to constrain low frequency foregrounds and essentially the largest scales in the CMB maps, where Planck was insensitive that we talked about earlier, the poorly measured modes. That's really what we're buying from WMAP. We're also using Haslam for 800 megahertz to constrain the synchrotron intensity. We are not including the intermediate Planck HFI channels or WMAP 23 gigahertz channels, and that is in some sense because they are too good. If we were to include those, then the whole astrophysical model would be dominated by them because they have much higher signal-to-noise ratio than LFI. And therefore, what we produce would then be dominated by the external analysis, the external processing, and we wouldn't be able to understand what the method does. So the goal is next now to include these ones, but in time domain. We don't want to introduce potential systematic errors. That's still in the data, in the other data. We want to have it in time domain so we can treat everything on the same footing. But it is worth noting and remembering that there could be systematic errors in our results now if something is wrong with any of these. We're now saying that these are actually good. We're assuming that there is no systematic errors up to the errors estimates that they have provided. So we're sort of trusting these analyses. So that is of course an issue. So what is the product from BeyondPlanck analysis? As I said, it's a Monte Carlo sampler, and as such, it's an ensemble of full samples and sets of parameters. It's all of those billions of parameters moving through the parameter space, essentially, taking into account all the different correlations. And that is illustrated here in this plot for some of the instrument parameters for the first 120 samples or something like that of the Gibbs string. And you can see that, for instance, starting from the top here, the gain scatters up and down. So this is the gain for a given 1 hour period of time for a single radiometer. It scatters up and down. There's a correlation length that's usually in the Markov chain, but you have 6 different chains, and they all seem to be exploring the same stationary distribution. So it seems to be working quite well. And then, of course, we have this gain here for every single pointing period in Planck and every single radiometer. So it's a big data set. Here's the same thing for band passes, and band passes is really the most difficult parameter to estimate in this because it's global. The band passes affect everything, and we can only do it with a standard Metropolis sampler. So this is really the worst parameter to estimate. Then we have white noise, correlated noise in terms of alpha and FNE, and all of these parameters are then sampled jointly, as I said. We don't only get the instrument parameters, but we also get sky models. And here, for instance, it's the CMB map that we get at then some given stage. Here's the synchrotron map in polarization and spectral indices in polarization. I can see that there's a lot of scatter here. One thing that is novel, and as I said, that is actually fundamental to making this fast enough is the fact that we're actually sampling the correlated noise as well. And that's what it's seeing here. So the correlated noise realizations is not described in terms of covariance matrix as it has been traditionally, but actually samples. So all of these are possible correlated noise realizations that are consistent with the data. And the advantage of this is, well, first of all, it makes the map making problem a lot faster. That's perhaps the most immediate advantage, but it also actually is the first time we're able to propagate correlated noise uncertainties at all angular resolutions. We are not limited to n size 16 or something like that anymore. We now have correlated noise at all angular scales, so that's nice. When we proposed this project, we didn't know how expensive this would be. We knew that we could do it a lot faster than 3 weeks per iteration. But was it 1 week, 1 day, 1 hour? We didn't know. And it took a lot of work to actually get this running and solve all the technical problems, and people will be talking about this during the week. I'd like to point out a few things here. And one is, in order to make this fast enough, one requirement for this to work is that we have to be able to store all the data in memory at once. We cannot go to the disk between each of this iteration. That would be too slow. So one of the novel algorithmic aspects in this analysis is that we actually compress the data and store it compressed in memory and just decompress it while we are analyzing the data. And so that actually gives us a big factor. Here it looks like it's almost a factor of 10. It's not really that, because in the original data volume for LFI, there's a lot of housekeeping data and other things that are not strictly necessary. But after cleaning up all of that and compressing the data, we actually managed to get the whole LFI data into 861 gigabytes. And that is a lot better than 8 terabytes. That means that you can store everything on a single compute node, speeding up the memory bus transfer and eliminating I/O, and everything becomes easier. With that in place, the actual total cost for a single sample turns out to be, in our case now, 8,200 seconds. So that corresponds to 2.3 hours per sample. This is running on a single 72-core node with 1.5 terabytes of RAM. So actually, this is pretty fast. This is not bad at all. We can live with this. So for the results that we are looking at today, we produced a total of 200 samples on each of 6 compute nodes. For a total of 1,200 samples, we had a burn-in of about 50 samples, so that leaves about 900 good samples for analysis. Of course, some of the parameters like the bandpass has a fairly long correlation length, so this is not a big set. In the next iteration, we would like to have about 2,000 samples. That's what we learned here. So 1,000 is borderline. But it does give us pretty good results for all the things that we want to estimate. The total wall production time for this run was 3 weeks. And we were tight on time, so this was actually started in November. Not November, October. So it's been running until now, essentially. But we have been through 2 main runs. The code as such was finished in August, and we've been through 2 main iterations. And of course, we will fine tune and refine as we go along. This is not the end. This is the first stable version, essentially. The total CPU cost for the main run was about 220,000 CPU hours, which perhaps sounds quite a fair amount. But when you compare that to the cost of the Planck analysis, then it's quite reasonable, actually. So if you're looking at the FFP, the full focal plane paper, you will find that simulating a single 70 gigahertz channel with all the components cost about 10,000 CPU hours. So that means that the current BeyondPlanck analysis of the whole LFI dataset, including component separation and power spectrum estimation and everything, has essentially the computational cost of 20 full focal plane simulations at 70 gigahertz. So it's quite reasonable. It's not bad. It's now at a level where you can actually run it in-house on a single compute node that is not too expensive. You don't need supercomputing centers to do this. We're not quite at the level where you can do it at the laptop, but give it another 5-10 years. Yeah, I wouldn't be surprised if it's possible to get pretty close. So as I said, what we are now getting out is these samples, and this is an illustration of the Stokes Q parameter for 30 gears. So this is a frequency map. And I hope we can see what's happening here. We're now scanning through a lot of these samples, and you can see that the whole thing is vibrating. And this is now our main product. We are providing you the community with mean maps, posterior mean. But really, that to us is only good for plotting purposes. What you really want for analysis is this set of samples. And so if you have an analysis you want to do, you actually analyze each of those samples as if that was the true measurement. And then you scan through all of those 900 good samples in our case, and you get the full posterior distribution, including all the systematic errors. Band passes, correlated noise, gains, and whatever. So this is really the fundamental new aspect of BeyondPlanck, the way of working with data in terms of posterior distribution, rather than a single mean map and a single RMS estimate or something like that, or a simulation. We now have a posterior distribution. And of course, as I said, we have posterior mean maps that we can then compare against the traditional estimates. At this level, if you were to put either DBC or the most recent NPipe results, so that's the final results from Planck, essentially, next to this, you would pretty much not see a difference. The effects are very subtle. But if you take the difference between them, then you're starting to see differences that you can interpret. So you can also start to see the way of propagating error is illustrated in this plot, where we now are taking the difference between two samples. This is essentially, then you see things like correlated noise here. You see bandpass errors in the galactic plane. You see calibration errors as this blue, red, blue thing over here. And all of this is now propagated within the sample set. 70 gigahertz, you also see some band passes playing around here. There's all these kind of structures. And the good thing is that you don't have to specifically account or propagate each individual effect. You just let the give sample explore the whole distribution, and it comes out in the distribution. So returning to the original motivation, we said that there were issues with the last Planck release. And of course, this has been improved with the latest NPipe results. So we have now two comparison points to compare the new BeyondPlanck results. And just to set the stage again, here is the poorly measured modes by Planck, the gain template that was provided by the LFI DBC. This sort of was LFI's understanding of the uncertainties in those maps. If you now take the difference between the BeyondPlanck and DBC and NPipe maps, this is what it looks like. And if you compare this map here, the Stokes Q and U parameters, to that template, the agreement is pretty spectacular. You can trace each of these effects very accurately, actually. So this indicates that whatever we have done with the gain modeling in BeyondPlanck, it does trace the known effect that we were hoping to find. If you compare it to the NPipe results, you can see that NPipe also did that. It's improved on the original one by adding a more detailed calibration model. And the residuals with respect to, or the differences with respect to BeyondPlanck are smaller, but clearly, I mean, it's the same kind of patterns, it's the same degenerate modes. And according to our understanding after this in BeyondPlanck today, one part of this, important part about this is actually the fact that there are degenerate modes in WMAP, in Planck, that is very difficult to trace because of the Planck scanning strategy. But when we are now using data from WMAP, those modes are no longer degenerate because those modes are sort of ruled out by WMAP. And therefore, the gain solution can then adjust and pick out the residuals rather than trying to put it into the CMB or the sky model. If you then compare with WMAP, what does that look like again? So this is again now the difference between 30 gigahertz and K-band, and this is what we had originally. This is 2018. This is what it looks like for NPipe, and you can clearly see that it's closer to WMAP than it was. Same kind of features overall, and this is what it looks like for BeyondPlanck. And if, for instance, you look at it like a plane, you can see that BeyondPlanck is definitely closer to WMAP here. And as I said earlier, K-band is not used directly in the BeyondPlanck analysis, so only Ka-band and higher. So it's not like we have just calibrated ourselves onto K-band. It's the information that we got in from the other channels that is improving this, and it does lead to consistency. And if you then compare this residual to the WMAP transmission imbalance template, which is also, again, a poorly measured mode in WMAP, you can recognize features here all over the place. So you can see this blue, red, blue thing here matches very close to this. Overall, it looks like we have cleaned up the LFI data very well. And what is dominating the residual here may be, of course, it's early to say, maybe then those poor measured modes in WMAP that we then need to account for through joint analysis of WMAP and Planck in BeyondPlanck, essentially. So it looks very promising. Right now, it's not like we have any obvious issues that aren't understood in this respect. WMAP and BeyondPlanck agrees very well with WMAP up to the uncertainties that WMAP provided. So what are we looking at in terms of frequency? So that was maps. What about frequency space or power spectrum space? Well, here is the TT, EE, and BB power spectra for 30, 44, and 70 gigahertz. And this is with a sky cut, and then you have signal dominated up here. So this is CMB essentially and foregrounds. And then you need to reach a noise floor here. And you can see that in the signal dominated regime, pretty much all of the three codes agree to a very, very high degree. So you shouldn't expect any revolutionary differences in terms of temperature or in the foreground analysis as such. It's going to be subtle. There are small differences we're talking about here. But there are interesting things happening at high frequencies, high L. And if you zoom in on that, you can see a closer look here. And if you, for instance, focus at the EE 30 gigahertz channel, you can see that BeyondPlanck, which is black one, has roughly comparable noise level overall as NPipe. It's a bit lower than 2018. But another striking thing is that the BeyondPlanck spectrum is actually much flatter than NPipe. And that indicates that there's less correlated noise in the BeyondPlanck data than there's in NPipe. And you can generally see the same thing, that BeyondPlanck is fairly flat. And the reason for that is that BeyondPlanck is not actually trying to estimate the correlated noise, or call it destriping, for each channel individually. It's everything done globally. And that means that in practice, the 30 gigahertz channel, when you're trying to destripe that, you're getting help from the 70 gigahertz channel in telling you what is CMB, what is foregrounds, and what is the sky. And that allows you to dig deeper into the correlated noise at 30 gigahertz. Likewise, when you're trying to destripe the 70 gigahertz channel, you're getting help from the 30 gigahertz synchronous polarization, for instance, and saying that this is actually sky and not noise. And so you can dig deeper into 70 gigahertz as well. When it comes to 44 gigahertz, that's a different story. And here you can see that we have more noise than either NPipe or DPC. And the reason for that is that, as we will discuss later and more tomorrow, what they found is that there is important systematic effects in the 44 gigahertz channel. In particular, there's one detector that appears to be broken during the second half of the mission, around 2 years into. That seems where it goes unstable. And Håvard will talk about that tomorrow. But the point is that what we have done then is, because this particular detector seems to be behaving in an unpredictable way, we have removed that data from the analysis, and that costs us a total of 16% of the data. We're taking out both of the radiometers in that horn, because otherwise you have temperature to polarization leakage, and so we rather take the white noise hits than having those systematics in the data. We also get, of course, temperature sky maps. So here's synchrotron, free, AME, and thermal dust. This is, of course, essentially just imported from HFI. This is because we have the 857 gigahertz channel, so there's nothing new here. This one is well, this has one as well, but this one has more information. In polarization, we now have, this is the first time, and this is an important point, this is the first time we have actually been able to fit both WMAP and Planck inside one parametric model and estimate spectral indices from both datasets at once. We have previously done it before, but because they have different calibrations, when you try to do it jointly, you ended up with spectral indices that was clearly not correct, like minus 3.5 or something like that. In this analysis setup here, we are in fact dominated by noise at the high latitudes. We're not able to get any estimates here. These are degenerate with gains and other effects. So, and in the galactic plane, there's residual temperature polarization leakage. So we also don't try to estimate this. But there are two regions that that seems clean and has enough signal to noise that actually we can get the meaningful estimates. So that's the North Galactic Spur and the galactic plane. And a nice result here that is interesting is going to be debated in the days that's coming along. They actually seem very consistent. We don't find any evidence for spatial variations. And if that is true, that's going to make the life of future polarization experiments much easier, because the spatial variations makes detecting BMOS much harder. We get estimates of the solar dipole without any particular special case. It's not like we have a dedicated dipole analysis. It just falls out of the analysis. And the dipole that we get is lower than what has been reported from LFI before. And that is largely because of this, gain template 30 gigs correction in Planck and mathematically. But intuitively, it's not surprising because we are using both WMAP and Planck data. And our estimate sort of falls between the two. But of course, it is actually fairly statistically consistent with all of them. And you can see our estimate is down here, which is roughly halfway between Planck and WMAP. Personally, one of the things I was most satisfied by seeing when this appeared the first time is the magnitude of the uncertainties on the direction, because that's been something we've been agonizing over in Planck for a long time. What are the uncertainties here? And they seem very small. Here, they come out to be almost an order of magnitude larger than what it was on HFI, and factor 2 larger than LFI. And I personally like large error bars because it's more conservative, and so I was happy to see this. The direction is, so you can see that we are in fact slightly different than the other ones, but we have also much larger error bars, and I'm very happy about that. So again, nothing special about that. It's just coming directly out of the Gibbs sampler. We, of course, get the CMB temperature maps, which is sort of the main science goal of the whole thing, so to speak. And we get not one of these, but we get the 900 of those, and that gives us the uncertainties with all these effects taken into account. We get the power spectrum, and this is now marginalized over all of those samples. And the black line here shows the residual between our power spectrum and the lambda CDM, as measured by Planck in this case, divided by our lambda CDM. And then compared with Planck and WMAP, and overall it looks pretty good. You can ask, is there something going on here? And that may be a 44 gigahertz band beam issue. Is there something here? Possibly, but overall, I mean, if you think about this in cosmological parameters, it is going to produce very consistent results overall. So one thing to note in the parameter model that we didn't discuss earlier is the fact that we don't actually marginalize over the beams. And that is a residual systematic effect that is important up here, that is still not accounted for. And we were hoping to do that. Well, we are going to do that in the future, but we didn't have resources or time to do it this time. So that's something that is coming in the future. Cosmological parameters. So this is now still not integrated into the pipeline. So it's not strictly true that it's end-to-end. It's end-to-end up to the likelihood. And then we are still using standard tools like CosmoMC to explore the likelihood given those parameters. In the future, we also want to have direct sampling where we don't actually go through a likelihood, but we just propose cosmological parameters. You compute a power spectrum using CAM or some tool like that, and then you use that as a metropolis accept or reject step, and then you can actually get away without any likelihood approximation at all. And that's going to be nice when you do tensor to scale ratio, because low L likelihood approximation is not trivial with the low L sample sets. Overall, the parameters that we get are very consistent with previous estimates, and you saw that from the power spectrum. The biggest difference is tau in this table, but this is because we're comparing against 2018, official one. If you compare against the most recent SROL2 or NPipe results, Tau here would be higher at roughly 0.058, 59, and then this would be 0.4 sigma, and that's essentially the level of fluctuations you expect just from noise between LFI and HFI, because we are not using HFI data, of course. So things are looking very, very good in terms of parameters. We do have larger error bars, and I would have loved to say that that is because we are marginalizing over more systematic effects, but the real case is actually because we're just using LFI and WMAP and not HFI. And HFI has a lot of pull in the regions between, say, L of 200 and 600 that LFI cannot match. So formally speaking, we do marginalize a much richer instrument model, but that is really negligible in temperature because of cosmic variance. So in the papers, we describe that the systematic effects account for 2 or 3 microkelvin in temperature, which is tiny compared to the other effects. But 2 or 3 microkelvin is not negligible compared to polarization. And that's really where the goal of all this is popping up. So with this sample set, we have now a way of propagating uncertainties into the low L covariance matrix and likelihood in a very direct way. Algorithmically, all we do is take the CMB samples that come out of the Gibbs sampler and smooth them, downgrade them to a low resolution, in our case NSide 8. We want to have as few modes as possible. And then we compute the covariance matrix again by just smoothing again the same thing, and then taking out the product of those maps. So that gives us a sample-based covariance matrix. There are some tricks here to reduce the number of modes even more in order to sort of optimize how we use the information in the sample set, because we're sampling and each sample is expensive. We cannot have too many modes, so we're trying to compress as hard as possible, and Loris and Simona are going to talk about that. But here you can see the covariance matrix in the form of a single slice. So imagine that you have this QU covariance matrix now, and you're just slicing it through one column, and you're looking at this pixel in particular. And what you can see is that here you can see the correlated noise imprinted because of the correlated noise samples. You can see the same thing in U here. But you can also see a lot of other effects as well. You can see the foregrounds is negatively correlated with that pixel and on the galactic plane, and that's happened because of both gain and bandpass uncertainties. You can see this thing here, which I think personally is the 141 gigahertz separation between the WMAP horns. You have gain residuals that you see these things here along the solar dipole. And all of that is now automatically built into the covariance matrix without any explicit modeling of each component. So this is actually the first time uncertainties from gain and band passes and really fine-grained foreground model has been propagated into low L likelihood in a very natural and easy way. We don't have to spend a lot of thousands of CPUs on covariance matrix evaluations anymore. It's all like done in 5 minutes, just smoothing those samples. Here's the CMB map. Of course, that is a bit difficult to interpret, but overall, I mean, you can see there are structures here, and hopefully this is then going to be residual fluctuations as described by the covariance matrix, and hopefully some CMB as well. It's difficult to interpret a map like that, so why don't we turn to the likelihood instead? And with these likelihood inputs, we can now use a standard brute force Gaussian likelihood. So where you have the CMB mean map here, you have the signal covariance matrix, which is then essentially given by the cosmological parameters, and you have the sample noise covariance matrix here. And you can just evaluate it, brute force, not think about it at all. If you do that with tau, this is what you get. And the colored curve here shows results from the literature, very recent ones. From WMAP is the dotted blue line here. A recent reanalysis by Natal of LFI and WMAP is the red one. You have Planck 2018 in green, orange is red, yellow. And the latest end pipe is purple. Eschol 2 is the orange one. And then the final BeyondPlanck likelihood is this black one. And you can see that it agrees well with the other ones, and it's significantly wider. And we'll get back to why that is, but of course, the biggest chunk is, again, that we don't use HFI. Yeah, as I said, we'll get back to that. But it is worth noting that this label here, it doesn't have, well, there's another curve here that says BeyondPlanck full sky. And that's actually not full sky. What that means is both hemispheres and a sky fraction of 0.72. And that's, if you do both hemispheres, we get this thing here, which has significantly higher power. Here's the same thing for R in terms of the scalar ratio. You have the black line, that's what we call the default, and then you have the full sky case down here in gray, and clearly here we have like a 4 sigma detection of R, which we're not terribly happy about. I mean, that would not be great if you didn't understand it. But before we address that, I just want to come back to the fact, to the issue about uncertainties. And to me, this plot sort of summarizes why we care about BeyondPlanck. This is why we did it all, really. What is shown here is the uncertainties on tau with different levels of marginalization. So in the blue line, it's what we show here is if you only marginalize over white noise and you think that you know what the TOD or the foreground parameters are, that's what you would get. So in practice, what we've done here is essentially to choose one realization of the foregrounds and one realization of the TOD, and then just sample a subspace of white noise. Then the red line shows the same, but now I'm also marginalizing of the TOD. The green one is the same thing, but now instead for something of foregrounds instead of TOD. And then the black line is when you sample over both the TOD and the foreground parameters. And this really is what combines all of these uncertainties into one model. And of course, that's what describes the real uncertainties in the problem. And so we have a nice way of propagating all of these uncertainties jointly now. But returning to the problem of the Northern Hemisphere, what is shown here from Simona's paper is different estimates of tau and R and chi-squared for different cases. And the important thing here is this full sky case. It's 74% of the sky, as I said, high tau, high R, but also a chi-squared that is actually less than a 1/10%, indicating that this, even with those very unusual parameters, is unable to describe this data set in terms of a statistically coherent model. And that means that either the data are non-Gaussian, it's non-isotropic, or lambda CDM is wrong. So it's a big assumption that goes into this. We were exploring this for a while and trying to understand the data set. And what we find is that if you then exclude the Southern Hemisphere, then everything looks fine. Then you have a chi-squared PTE of 16%, which is just perfect. So as I said, I mean, we're only using the Northern Hemisphere for now. But what happened on the Southern Hemisphere? That's the big question. And to see that, one of the big advantages of what we do now with this approach is that we can actually inspect every single parameter in the model and try to find what the problems are. And this shows, I think, most clearly what the problem is. So this shows the correlated noise at 44 gigahertz. And you can see these massive fat stripes here on the Southern Hemisphere. That is clearly not correlated noise. It's picking up something else. We don't know what it is, and we're working hard on trying to understand that. But clearly, the Southern Hemisphere has issues that need to be solved. What we do know is that it appears to be associated with a gain model. And so two different hypotheses is that, okay, perhaps we messed up with the processing mask. Could there be some small point sources or something that messes up these rings? We have played around with masks and haven't found anything striking, but it's still a possibility. The other one is undetected gain jumps. Every now and then, the instrument does something. And if there's a gain jump that we don't know about, it's going to sort of smooth out the gain over that jump, and that could produce something like this. We don't know yet, but this is work ongoing. The other problem that we're left with is the noise model. So let's start out to illustrate this, a good channel. So this is 70 gigahertz. And for 70 gigahertz, what we have assumed about the noise is that it follows a standard 1/f noise model. And what we're now doing is fitting those parameters hour by hour throughout the mission. And what you can see here is that the noise parameters actually vary a lot over the course of the mission. Here, for instance, we can see the effect of the so-called Sorsen cooler switchover. There was an instrument issue that had to be changed, so coolers has been changed, and that changed the instrument quite a lot. But you'll see that the noise model in terms of the chi-squared is actually pretty good. Even with all these variations, the 1/f noise model performs well, and it's able to describe it. At 44 gigahertz, what happened now then? At 44 gigahertz, the same is not true. There's a lot of variations in the noise properties, but here you can see the chi-squared is actually, on average, 2 to 3 sigma high. And it does vary a lot. So here it indicates that the noise model at 44 gigahertz channel is not working sufficiently well at all. And even worse case is the one that we already touched upon, the 26S radiometer. Here you can see that the instruments worked very well throughout the first half of the mission, and then boom, suddenly it becomes unstable, and you have 5 sigma fluctuations with varying amplitude throughout the rest of the mission. So that is why we have chosen to exclude all of that region here, all of those data for BeyondPlanck, at the cost of increasing our statistical errors with 16%. So what actually happens? Well, if you look at the power spectrum in time for these channels, so this that's what's shown in black here. The 1f noise model corresponds to these curves here. And you can see that it doesn't really fit very well. There's an excess power in time scales between, say, 10 seconds and a fraction of a second, 10 to a second, something like that. At 26S, it's even more striking. So it looks pretty good for the first half of the mission. And then suddenly you get a bigger excess in the intermediate range. So as I said, we are fitting the noise model with a 1f profile, but that doesn't work for the 30 and 44 GHz channels. It's like a 2 or 3 sigma excess at every single hour. And that corresponds translates into excess noise in between 1 and 60 degrees in the sky, which is important for polarization analysis. So this needs to be fit. We need a more general noise model that actually is able to account for this. And that's going to be an important goal for future work. It appears to be non-thermal in origin, could be an electrical issue. People are working on this. And input from other people would be much appreciated. We want to solve this. And we're talking about the future. So BeyondPlanck has now sort of reached the end of life for the current project. We have managed to establish the methods that we promised to do. It appears to be working very well on LFI. It has highlighted some problems that's still to be resolved, and those will be addressed in the near future. But really, it's also important to note that we have only used a very, very small fraction of the available data set. We have only used LFI in a few HFI channels and a few WMAP channels. In order to constrain the whole model and produce the best possible representation of true sky, we want to include all of this information. So BeyondPlanck has essentially established a framework to do this global analysis, but now it needs to be populated with complementary data sets. And that includes things like HFI, WMAP for Fires and Derby. But we also hope that proprietary experiments will be interested in using this framework and perhaps collaborate across experiments to produce better and better data sets. So this is the hope. This clearly will need to be a community effort and rely on active participation from various experiments. And organizing this is what the Cosmoglobe project is about. So Ingun will talk about that on Friday. But think about BeyondPlanck as establishing a framework, and then Cosmoglobe actually putting this into practice for a global model across the community. For this to be used by the community, we actually need to make the code available. And the current computer code, the main code, is called Commander 3. That is a direct generalization of Commander 2, which people know from Planck 2018. And that is now publicly released in an open source license, which means that everybody's welcome to download it, compile it, use it for your own work freely. But because it's an open source license of this type, that means that if you're publishing, you should then feed your contributions back into the community and helping other people with their own problems. So building a community is what this is about. We have established products, software, and documentation. A lot of work has gone into that. And all of that is accessible through BeyondPlanck.science. And I would like to point out some caveats, and that is, first of all, that all this software is provided as is. We don't guarantee anything. If there can be bugs, and likely is bugs in the code, you need to use it on your data set, test it, validate it, and make sure that it works for your case. Also, this is a software platform for cutting-edge research. People are adding features all the time, and that means that it's really in a fluid state. And you shouldn't expect it to be a black box that you just download and works for everything. It's like a tool that is constantly evolving. I would also point out that we don't have a help desk. We are nobody paid to sort of provide help, but we are more than happy to help out with people trying to get this to work. But that is, of course, remembering that we are scientists and we would like to understand what the universe looks like. And so the best way of actually doing this, if you want to get help for a given project, is to propose a research project with some of the team members to help you if you want to get it running. So the collaboration aspect is important. What we're trying to do here is build a community where people are working together to solve problems. So that sort of summarizes the BeyondPlanck. And just looking slightly ahead, the rest of the week now is going to spend on making detailed presentations of everything I've been talking about. On Monday and Tuesday, there will be a tutorial giving a more hands-on introduction to how you do this in practice. There's a lot of online resources. Most of it is accessible through BeyondPlanck project, all of it, I suppose. And I would like to point out this discussion forum. If you have questions, this is the right place to sort of post those questions and make contact. So again, community building. Commander is available with documentation. The Cosmoglobe webpage is going to be the future hub for all of this, hosted by University of Oslo, and that's going to then have a long-term lifetime, whereas BeyondPlanck, after the end of the project, may get outdated because we don't have funds to update it. So this is the future is Cosmoglobe, so to speak. Products will be available through the Planck Legacy Archive. Yeah. So to summarize, BeyondPlanck, the way I see it, has now successfully implemented a framework for global end-to-end Bayesian and CMB analysis and demonstrated that using Planck LFI. Some of the important advantages of this framework are, so first of all, joint instrument and foreground modeling, and that gives you more robust results. You can use information you have learned about foregrounds to improve your instrumentation and vice versa. You get end-to-end error propagation, and that means more reliable uncertainties, and that was, I think, illustrated in the dipole. Really, it's nice to see uncertainties that you don't need to think about what are the systematic effects. There are no systematic effects here, or systematic uncertainties here. It's just we have made everything statistical, essentially. It's all built into the model. Models are physically motivated, and that makes it more easy to interpret in terms of dust or synchrotron or 1/f or whatever. Multi-experiment analysis, I think it's hard to understate how important that is, because every single experiment I know have their own peculiarities, its own degeneracies. It's very, very difficult to analyze each individual experiment. But the mode that is degenerate for one experiment is not necessarily the mode that is degenerate for another experiment. And WMAP and Planck are brilliant examples of that. If you use information from Planck, you can clean up WMAP. If you use information from WMAP, you can clean up the Planck. And that same thing holds for any other ground-based balloon-borne experiment as well. The large scales can then easily be taken from this one, and you can then spend your time focusing on the small scales where really your ground-based experiments is unique, and then take the best of all these experiments. Multi-level goodness of it, again, difficult to understate how important that is, because that allows you to trace systematics throughout the pipeline, and that's really what has been allowed us to identify the issues with the 44 GHz channel. No intermediate human interaction, less room for mistakes. High computational efficiency, can run on inexpensive computers. We have it in-house now, a single compute node, you can run the whole LFI analysis. And now, as I said, generalize, populate this framework in many more data sets, hopefully both public and proprietary. And that's Cosmoglobe is the future. So that sort of concludes my summary. Thank you very much. And before I end, I would just like to go through a few more slides. And the first is, again, revisit the BeyondPlanck collaboration. I would just like to point out that this project is really dominated by young people, the postdocs and PhD students. There are 10 PhDs and postdocs, and they are really the ones who have carried all the heavy duty work here. It's been spectacular to work with this amazingly talented group. Funding, this would not have been possible without the Horizon 2020 program. Fantastic support. I'd particularly like to thank Diana, who has been our EU contact person, very, very helpful throughout the process. There's also support from collaborating projects, 2 ERC projects that has provided complementary aspects in terms of algorithm and of course Cosmoglobe, as they already see. So we are a bit over time, but I think we should allow a few questions if there are anything, but mostly I would like to defer questions to the individual specialized talks. Thank you.